as usual, I'll recommend you to watch these videos first. If you're done, let's get into it. In previous videos, we're playing with Q or electric charge particle or electric charge object that here, by empirical evidence, we see that charge is conserved. So here, we have charge conservation concept, and at the end of this conservation law, we can formulate the Maxwell's equations just like these four set equations. Here, this set of equations creates some kind we know as Maxwell's field or the electromagnetic field that is wave representation of light in quantum mechanics. But in this video, we focus on M or mass that generate the other side of physics as continuum mechanics. Here, we recall Newton's second law of motions as this equation, which P here relate to this multiplication between mass and the vector of velocity, and this formulation only valid for each one single particle, which P is another definition because it's basic of kinematics that told dynamics or some kind of bridging between kinematic and dynamics. That's why here we won't use X as a position which told us about state only about its position in our system. And here, we are not using X explicitly because in continuum system, there is mass-moment definition as this that characterized mostly in rigid body. So in this video, we want a generalization. So here we define the momentum vector P is equals to this integral inside region omega that, as I told you before, the position is inside these two states of the system that tell us about position for magnitude or direction of some kind momentum density. And then if we take the first derivative with respect to time to P vector here, we can use Reynolds transport theorem or by simplification as transport equation that generalize the boundary or the region of omega that can depend on time will equals to this integral. Here, the term divergence comes from this product rule of partial derivative that combine in nabla operator, and the inside of this divergence create some kind of tensors by this metric representation factor multiplication that will be our discussion in next video. After I rewrite the equation, if we take the first derivative of mass is equals to 0 for M is total mass inside system or mass conservation inside system, we will get this continuity equation that effect to F vector here is equals to this integral. And here, this what we use in continuum system maybe as fluid. So here, this equation is basic, especially in fluid mechanics. For example, a static fluid case, when velocity vector is equals to 0 vector here, as we know, F vector is equals to 0 vector too. But here, if we build our system by some kind of container filled by some kind of fluid has rho as its density, although this equation stands true, the gravitational acceleration here is non-zero vector. So what inside the F vector that create F vector is equals to 0 vector? Here, we can build this 0 to this integral, which to force this equation through, the relation of integrand will be as this, and this F vector come from partition of fluid that creates some kind of relation as this infinitesimal equation. Here in the system, if we take lower layer of fluid, of course in minus y direction, then the magnitude of F vector here will be greater and greater. So here, F vector may be related to some kind of gradient of some scalar function. So the gradient relation relate that if we take lower and lower level of fluid, the magnitude of F will be greater and greater. And let's say the scalar function here as P, usually known as hydrostatic pressure, that if we take area, let's say A, that face to some direction, and on that direction we have force F, then P here is equals to this as pressure that we know as hydrostatic pressure. So for summary, we have the equation of force by kinematics as this, and for dynamics relation here in blue, we get this integral which integrand inside there is P as hydrostatic pressure that will be basic in continuum mechanics, especially nabla P plus this external F factor related to fluid mechanics in physics. And that's the basic formulation and concept about continuum mechanics that have example in fluid mechanics. I hope you enjoy this video. If you like this video, don't forget to share and subscribe. If you have any questions, please drop comment below. And that's it. See you later.